Okay, welcome for the benefit of the recording to Code Along. It's labeled as Code Along 10. It's the Code Along in week 10. It's actually the 9th one because we didn't have one in week. Sorry, I'm laughing because someone put a joke in the chat, but I'm not going to say what it is on the recording. You had to be there. Yes, this is the 9th code along, which is the one in week 10, and labeled as code along 10 because we do numbering in strange ways in this course. If you're watching the recordings afterwards, you might want to go back and watch the previous two first, because this is carrying on with the same data set, but I'm going to talk about it anyway now for people who are here live. So don't worry if you missed either of the previous two, I'll talk about it. But we're going to be looking at our data set about pubs in the UK. And we're going to be looking at doing some modeling on this data set. So hopefully you can see my screen now on RStudio Cloud. I'll just no, that didn't work. Just full screen it. There we go. And I'll just zoom in as I usually do. Seems about right. I don't think I usually do full screen actually, but anyway, that's too far though. That's way too far. That's better. Cool. So welcome to the Code Along. I have started running this earlier today, or yesterday, because unlike normal, I wanted to make sure if you were there last week, you might remember I was having lots of trouble with the map. Even when I left this running for ages, I couldn't get the map of the whole of the UK to knit on RStudio Cloud. I think there just might have been too many regions somehow for it to cope with, or I don't really know what was going on, to be honest. But I managed to make it work when I restricted to Scotland. So that's what I was fiddling around with in this repo. So just to remind you what the data set is, the response variable that we're going to be interested in is the number of pubs per capita. And the potential explanatory, well, the other variables, we've got some of which we can use as explanatory variables, are the area code, which is a it's more useful for joining data, but it exists and is a code for each district. We've got the area name, which is the name of each district. We've got the number of pubs in each district, but we probably don't want to bring that in if we're doing the pubs per capita. We'd expect maybe some correlation between the number of pubs per capita and the number of pubs, but that's not very informative. Population of each district, which UK nation each district belongs to, the median weekly pay, the area of each district to mean high water level, whether or not a variable is coastal with this slide. So I was trying to make this point last week with the map and it didn't work, but I can show you now. Coastal is defined as has some land that's below mean high water level. That doesn't necessarily agree with what you would define as coastal. So in particular in Scotland, I think you see my cursor, this little region here that's kind of got green on either side, but there's a little blue region. It's divided down the middle by a river. So this is one region. That's Glasgow. Glasgow isn't usually thought of as a coastal city, but it's coastal according to this. Whereas Edinburgh actually is coastal, and Edinburgh is there. Edinburgh has a seaside. I recommend going to Portobello if you haven't made it there already. And then, I closed the document I wanted, but I wanted it in the viewer pane anyway. So let's just take the opportunity to redo that. So the other variables are population density, number of people per square kilometre, and the life expectancy of people of binary sexes as measured by the ONS. So what we did last week was we looked at fitting a simple model. Well, we looked at where NAs were in the data. So we worked out in particular that a few of these variables are just missing for Northern Ireland. So I wrote this up here. So median pay is not available for Northern Ireland and also for two very small regions, City of London and the Isles of Scilly. Whether or not something's coastal wasn't well defined for Northern Ireland. You could make the calculations, but if you tried, what you found was that nowhere in Northern Ireland was coastal, and that's not true. Life expectancy was available, it just wasn't available for this selection of places, or the City of London, the Isles of Scilly, and this selection of places that don't exist anymore. Well, they exist. You can still go to East Dorset, but there's no council for East Dorset anymore. So we did a pairs plot. We looked at these different variables, and I was saying that this is a plot that's useful in your, I've included it here because this is kind of an educational resource, but if you're actually writing up a data science project, you probably don't want to include this plot because it's messy, it's hard to customize. One thing I noticed, actually, I didn't notice last week, is that the way it deals with colors is annoying. Because if you look here, Scotland is green, and if you look here, Scotland is blue, and Northern Ireland is green, because it's just using the default ggplot colors, and it's separately scaling them for when Northern Ireland is and isn't present. So that's confusing, and that's a pain to try and fix, I think, with a ggpairs plot. But we did notice from this, so that there's two outliers here. We removed those outliers because in this case, there are good reasons to remove them. So the reason we remove them is that they have, they're both, well, the Isles of Scilly are quite isolated and have a small population, which is going to force up the number of pubs per capita quite a long way. So it's not really representative of what the density of pubs would be like if the Isles of Scilly theoretically were larger. And the City of London is, most of the people who go to the City of London on a daily basis don't live there. Over 500,000 people work there, and only about 8,000 people live there. So these are outliers with features that make them different from everything else, and that's why we remove them. What you cannot do, and I can't emphasize this enough, what you cannot do is remove values from your analysis just because they're outliers. And in fact, if we look down here, here is an outlier in terms of area. That's the Highland Council area, and we didn't remove that because there's no real, the Highland Council area happens to be really large, but it's not fundamentally different from any of the other council areas in Scotland. So we need to leave that in. We might later on consider cropping that out of a plot, because maybe there's a linear trend here, some sort of linear association here, or some sort of at least association that's hard to see in this plot. And we might consider removing this point purely for the purposes of the plot, using, say, chord Cartesian, using like chord Cartesian. But we don't want to remove it from our analysis because there's no reason to. And similarly, there's some outlying points here, but there's no reason. We could investigate them, but I don't think there's any particular reason to remove them. Okay, so, and then what we tried was a univariate regression, and we got that there was some sort of relationship, some sort of negative relationship. In particular, for every £100 a week that median pay increased, the predicted number of pubs per capita decreased by, oh, that's a typo. I need to fix that. So that should say the predicted number of pubs per 10,000 people. I will fix that in last week's one as well, because that's also there. Okay, so we found the predicted number of pubs per 10,000 people decreased by about 0.823, and that shouldn't be minus either. Something's gone wrong. I need to fix some of these things. It doesn't decrease by minus 0.00083. Anyway, moving on. So what we could do is consider more terms. And one thing that might be quite useful to do is just to fit the full model, to fit every term that plausibly could make sense or plausibly could be useful. Oh, I'm just gonna, one sec. I'm just gonna stop sharing for 1 second while I open the chat. Oh, right. Someone's saying, does the graph say Glasgow and Edinburgh coastal? Yes, it did. I don't know what point you said that, but yes, Edinburgh is coastal. So cool. Let's have a look then at the let's have a look at our other variables. So what might be useful? Has anyone looked at, can anyone think of what we might want to do to make this kind of generalizable? So instead of just fitting a model and like modifying our data, what could we do to make it so if we wanted to do, say, a test train split or do some cross-validation or anything like that, what would be a useful thing to do to make? I'm trying to think of any clues I can give beyond that. Yes, there we go.
A fair amount of clues.
Yeah, workflow. There we go. My next clue is going to be begins with W because I was running out of things to say. Yeah, we can make a workflow. That's a really good idea. So a workflow generally is made up of two things. It's made up of a recipe and a model. So we made a data set called pubs reduced, and I'm only going to work on that data set for now. Oh, go away. By 10:39 today. Oh, well, that's helpful, isn't it? Okay. We're going to have to pause this for now because I'm going to get kicked out of my computer. So
David will take questions.
David will take questions for now.
We'll see you in a sec. Do we have any questions while Alex's computer is being forcibly restarted? Please post them in the chat. They don't have to be about this. They can be about anything. In fact, I'll put the recording on pause. Awesome, we're back.
Oh, David started just before I needed to sneeze. It's not his fault. He didn't know. Yeah, welcome back. My computer needed to restart in case you didn't get that from the end of the recording. I don't know why. But anyway, we had a question in the break, which I'm going to take now. We were talking about workflows, but just as we were about to go into it, someone says, when you want to predict a variable from multiple variables, you usually use plus. I've seen a section that uses star instead and wondered what that does. It's a really good question. So star includes both these terms and the interaction terms. So the easiest way to think about this is when you have a categorical and a continuous variable. So I'm going to share my screen so you can see this. That's my screen. I'm just going to do a slightly simpler version. Then we're going to talk about workflows in a sec and just add everything basically. But let's have a look at setting. I'll just for now create some other models. So if I just tell it to run all of the code that's above. I probably should have told it to skip doing the map, but oh no, it didn't take too long. All right. So what I'll do while it's all running is I'll add our categorical. So the reason I added the coastal was so that we'd have a binary variable we could add in. So we could fit this model. And what we'd see is if we did a glance at mod plus, no, we want a tidy version. I want to apply tidy to mod plus. What we'll see is that we have our median pay term and our coastal term. So what this is doing is it's saying, okay, we've got a slope for median pay. We've got an intercept in our term. We've got a slope for median pay. And we also can shift this. So we've got this sort of regression line. And then we can also shift this line up and down depending on whether or not coastal is inland. So it can only take two distinct values, but we can sort of add a little shift or subtract a little shift for the intercept. So that's one thing we can do. The other thing we can do, though, is we can put a star here. So what that does when we do a tidy of, oh, I should have called that mod star. doesn't matter. But, if we do a tidy of mod star, I'm going to remove that anyway. So we now get this last term. This is the interaction term that it's adding in. So what that's saying is, okay, we can modify the, we have a slope term and we have an intercept term. We can shift the intercept for coastal if it's inland. So we've got a baseline one for coastal and we've got a shift on it for inland. And we've then also got a change in the slope for coastal and land. So that essentially means we're setting two distinct regression lines, one for coastal, one for inland, and they're completely free. So whereas before we're setting two regression lines, but they both have the same slope, this time we're just independently fitting two regression lines essentially. But we're still taking, when we calculate this and calculate the standard errors, we haven't talked about what those are yet, but all those things, we're still taking one as the baseline. So the fit is as if we were fitting two independent regression lines, but exactly how we're doing estimates and so on is not that way. So the reason you use a star, the other thing you can do is put a colon, but you shouldn't. And I'll show you why not. So if what that does on its own is, this is going to be unpleasant. So, okay, so it's fine sort of on its own. What it's done is it said that there's an intercept and there are two different values of the slope for coastal and coastal inland, but we're not allowed to change the intercept for these two terms. That's essentially what's going on there. It's been a bit weird because this time it hasn't chosen a baseline because we didn't put in an explicit median page in 17 terms. Let's put that in. And look at what that looks like. So what we're saying there is that we force the intercept to be the same for both terms, but the slope to be different. And it's rare that you want to do that. Just as it's rare that you want to force the intercept to be 0. It's possible to do that in R, but there's very rarely a use case for it. It would tend to be something where you are absolutely 100% sure that 0 should map to 0. And there are so few use cases for that that it's almost not worth trying to think of one. There isn't a name for these types of operators explicitly. They're just operators that go into, there's a name for this kind of setup in R, this kind of thing. It's called an R formula. And these are just operators that apply within formulae, but they're not, there's no, I don't think there's a name for them, like formula operators, I suppose. I don't think there's a name beyond that. And of course, all of these are used as other things in other contexts. So colon is used for making vectors, star is used for multiplication, all that kind of stuff. If you have two continuous variables and you put a star in between them, essentially what that does is it fits a regression where your variables are, what's it do? It fits a regression where your variables are like, you've got an intercept, a slope with respect to one variable, a slope with respect to another variable, and kind of a slope with respect to the multiplication of those two variables. It's a bit weird. And you could sort of plot what the surface of regression is doing in that case. But it will essentially control kind of what's happening on the diagonal relative to, yeah. It's a bit weird.
So this is why we call it an interaction, right? Because it's when you have two things that are happening, it's going to change the slope because both things are happening. So you have them when they're separate with the other ones held constant. And then the interaction is when both things are happening. We're also going to allow our model to shift it slightly when, or a lot, it depends on the estimate, obviously, dependent on if both things are happening. So it's an interaction.
What we're going to do now is try, so you could theoretically fit an interaction, like third level interactions and so on. One thing Mina says in the videos is that while you can, perhaps you shouldn't, because the interpretation gets quite hard at that point. What we're going to do is fit a model that has most of the variables in our table, we're going to do a workflow where we fit most of the variables in our table as a model here. So we're going to do an additive model, so no interactions, but just take everything-ish. So let's make the recipe for that. Let's say our recipe. So our recipe is going to be, let's call it pubs.rec, and we always start a recipe with the recipe function. So recipe, remember, is something that we can apply to multiple different sets of data.
Does this relate to our workflow that we were asked about before?
Yes, it does. So this is the first step in making a workflow. So when we eventually make a workflow, we make a workflow by starting with the function workflow and then adding a model to it and adding a recipe to it. So we need to make a recipe first. So a recipe is a series of steps that you will always apply to data to sort of prepare it for fitting the model. And it's also where you specify sort of the formula that you're going to apply. So the recipe function starts with the formula, and the formula is going to be pubs per capita against everything. And we don't actually want to do it with everything, but the way we're going to get around that is our recipe is going to specify removing certain variables. And we also need to give it data. And you might think, well, hang on, isn't the point of this recipe that we can apply it to lots of different data sets? And you'd be right, it is. But we need something to at least give it the structure of the data that we're going to be working with. So something that has the right variables that have the right types. Otherwise, it's not going to really know what to make of any of this. So it doesn't really matter what you put as the data here, as long as it's something that has the right variables and the right values. So in our case, pubs reduced is what we're going to use here. So this is the one where we've removed the outliers but done nothing else to it. And the reason we're doing it that kind of split is the outliers, I'm going to say we never want to include in our analysis. But it might be that we want to. So one of the things we're going to do is remove the Northern Irish data. And the reason for that is that Northern Ireland is missing from 3 other variables. And just to make our analysis simpler, if we get rid of that, it will avoid having problems with the, firstly, it will avoid having problems with the categorical data. If we add country as categorical predictor, there'll be slight issues if certain variables just aren't there for one level of that predictor. And also the fact that we just don't have the other data for Northern Ireland suggests we probably need to do something a bit different for Northern Ireland anyway, whether that's finding different data, or which probably won't line up exactly with the data for Great Britain, or it might be that we need to just look at different predictors if we really wanted to predict number of pubs per capita, and so on. So we're just going to filter out the Northern Irish data for now. What we are going to do first is we have said that we want to regress. So I mentioned before that the way we're going to get around the fact that we've just told it do a regression on everything is we're about to remove some things from our data. So we're going to add a step to our recipe. So a recipe starts with the function recipe, and then it's every function that's piped on afterwards is one of a series of steps. And the first step is we're going to remove some variables. So can anyone think of a variable that we, I'll just quickly show you in the console, a glimpse of the data. There we go. Can anyone think of any of these variables that we do not want to include as an explanatory variable?
But for what are we trying to predict?
So we're trying to predict pubs per capita. So one thing I'll just quickly say, we don't need to specify that we don't, obviously we don't want to use pubs per capita. That would be nonsensical. Yes, name. Against the tilde dot means against everything but what's on the left-hand side. So you don't have to do that. And in fact, if we tried to remove pubs per capita, it would give an error because we'd have removed the predictor variable. Response variable, rather. Yes, name is a good one. There's nothing we're going to get from name. There's a different name for every area. You could maybe get we could do some feature engineering here if we wanted to. So for instance, does it start with a C? We could take like first letter maybe as a predictor, or, length of name or something like that. Does it have the word county in it? I don't know. It's difficult to think what we could do there, but we could do some feature engineering. So yeah, and that's the main one I can think of. Like you could say, is it an authority area? as a very, very rough proxy, it doesn't really work. Nah, I can't think why. All I was thinking was you could have one for like things that have county or shire or something versus things that don't. But the way local government works in England, that doesn't really work. It doesn't. I was thinking it's a sort of urban-rural split, but it doesn't really work because
if you're trying to pick pubs, would it make sense to say, is it in the north?
Yeah, you could do it in the north. You'd have to manually feature engineer that. You'd have to know, because these data, annoyingly, don't have. You'd probably need a lookup table for that, but you could do that. Yes, I'll just take the other things in the chat. So area code, yeah. UK English region would have been a useful thing, but it's not in the data set, and you could get it. There's definitely lookup tables for converting area codes to regions. The ONS used to use a system where this was hierarchical, so you could tell which region it was based on the beginning of the code. But apart from like England, Scotland, Wales, Northern Ireland, you can't do that anymore. They're just numbers. So what's the difference between step RM and the minus sign? Step RM is when we're making a recipe. That's the main difference. So it's equivalent roughly to select minus this. It's just in the context of making a recipe as opposed to in the context of just working with data directly. So area codes we want to remove. I'm going to remove two more. So I'm going to remove the number of pubs, and I'm going to remove the population. I'm going to remove the number of pubs because that's, well, they're the two things that I divided by each other to get the pubs per capita. So it's not really all that informative to try and use them as predictors, because numpubs is directly calculated from the pubs per capita is directly calculated from those two things. And we'd kind of expect population, we might get something interesting going on, but that's probably more reflected by population density. Step RM would also work more generally, sort of, but I don't think you can use Step RM outside of the context of a recipe. So I don't think you can use it even if, if you were just doing data analysis. It only works like if you're building a recipe. That's sort of the point of it. I'm actually going to remove one more. I prepped this and I didn't remove this one, but I'm going to remove it. I'm going to remove the area as well as a predictor, because that's essentially, we've already got the population density and the area isn't, it was calculated from the population density, but I'm not sure anything particularly useful is going to come from the area, because you can have very large areas that are like urban. And the area of a council area is determined mostly by, it's either a function of population density or it's just that's where some politicians drew the boundary in the 1970s usually. And that's not always very informative. Sorry,
I have a question for you.
Yes.
If you've been calculating two things, right?
Yeah.
One's made up of something else.
Yeah.
Aren't they going to be very correlated with each other, right?
There will be some correlation, yeah.
Some correlation. And won't that affect your modeling? Because we want things to be independent, right? We don't want them to be sharing information.
Yeah. Ideally. So what we've done here is removed anything where that's true, I believe, or at least where there isn't some alternative thing. So both pubs per capita and population density haven't been calculated using the population, but there are other things that are separate involved in both of those. So that should hopefully mean that they're not too correlated with each other. But they would be negatively correlated, if anything, because as population goes up, one of those things goes up, one of them goes down. But that's one reason to avoid including, say, both the area and the population density. So yeah, ideally your response variables are your explanatory variables, I always get the wrong word, are uncorrelated. You can't always guarantee that, but ideally they would be. And it's better to avoid things where there's going to be a lot of correlation, because that will mess up what your model's doing, because it won't fully capture the effect of what's truly like. You could include one or the other, but including both will kind of confuse it a little bit. It will make it not really sure which one of them is contributing and is causing not causing, but is sort of, it will kind of have to pick between them when it's trying to work out what their model parameters are. And that's not necessarily helpful. It can lead to some counterintuitive results. So it can lead to like negative signs in the model where you'd expect things to be positive.
Yeah, it can just mess with your estimates, and then that messes with your interpretation as to what's driving what.
Yeah.
So you typically don't want it.
Yeah, exactly. So yeah, I'm going to remove the area because, as I say, it's as just a random example. I know too much about local government in England. As a random example, like they kept merging some small areas into large areas throughout the last couple of decades, and that doesn't really reflect anything about the area. It's just they decided that those areas should have a bigger council now, and so that council serving more people in a bigger area, and that doesn't really reflect anything inherent about the area. Why do we want to keep the coastal? Good question. Because I'm interested in essentially in whether or not there's no particularly good reason to think that pubs, well, I say that. So, you know, maybe people are more likely to go to the pub when they're on holiday, and people are more likely to go within the UK. If you're going on holiday in the UK, people often go towards the seaside for the holiday. Would be my sort of rough justification of that. Now, that's a bit, it's not perfect, and the problem there really is with the data. I don't have a good measure of like how coastal, you know, what I might like is say a continuous explanatory variable that was like population of that area that lives on the coast, or proportion of that area's population that lives on the coast. But I don't have that data, so it was just a rough proxy for that. And as I say, it includes things like Glasgow. If you try to go to Glasgow and go to the beach, you'll be a bit disappointed. Glasgow is a lovely city, but does not have a beach. Yeah, it's because I'm interested in seeing whether there is any relationship between those two things, and maybe it is going to be useful for the model. No worries. So the next thing I said we wanted to do was filter out Northern Ireland, for the reason that the data are just very different and there's a lot of missing data for Northern Ireland. And that's annoying. It's annoying that some of the data aren't more correlated, but that's an issue again with the data source rather than necessarily anything we can do anything about. Let's filter that out. So step filter is another one. I'll come to the question in a sec. I'll just finish the model. The final thing we want to do is create some dummy variables. So you don't always have to explicitly do this, but it's a good idea to do it when you're building a recipe. When you're fitting a model sort of initially, you don't have to worry about this quite as much, but we'll create some dummy variables which represent what are called the nominal variables in the data. So that means anything that's factor or character as its data type. And that's because, you know, you can't do, if you're fitting a model, you can't do the predicted value is, you know, 15 plus 3 times England. That doesn't make sense. So what you do is create sort of yes/no variables for each categorical thing. So this is when we build a model, how do we account for the fact that correlation is not causation? By bearing that in mind, essentially. So all we're doing here is finding correlations. It's in the interpretation that we account for that. Fitting a model is purely a mathematical thing. It is essentially plugging things into equations. And you can do lots of things by plugging things into equations without necessarily thinking about what they do, and in fact, or what they might mean in the real world. And it's a bit glib, but pure mathematicians frequently just do things with pure numbers and don't really worry about implications to the real world. It's in our interpretation, we have to think about that. Step filter and step RM are slightly different in the same way that select and filter are different things. Step RM is removing columns from the data. Step filter is filtering rows. So it's saying we want the ones where the country isn't Northern Ireland. Okay, so the next thing is we want to fit a pubs. We want to fit a model. So we've got our recipe. Let's define our recipe. And we next want to tell it what the model is. So the model, this is going to be hopefully a little bit familiar. We're going to do a linear regression, and we need to set the engine, which is LM. I think I said this last week. The difference between these two steps is that you can fit different type. All this is saying is we want to predict a line from, we're going to get a linear predictor with this thing. So what we want is not a logistic regression, for instance. We literally want to predict as a line. The set engine is telling it we want to do a normal linear regression. We haven't talked in detail about what that means, but it's one particular way of, I should say workflow. It's one particular way of mathematically fitting a model, but there are other different ways to try and fit a line to data, essentially, that we're not talking about in this course, and that are maybe a bit rarer than using LM, but have reasons why you might want to use. Okay, so then for the workflow, we will do workflow, pipe into, and we add the model. So this is just a standard series of steps. We add the model, and then we add the recipe. And we have a workflow. So now it's really straightforward from now to start doing things like a test train split, and to apply a model to both sides of our split, and to maybe do some cross-validation. So let's, and by the way, we should have done the test train split before we did any of the stuff last week that involved what we're now going to have as our training data, but we didn't, so never mind. Okay.
Why is that the case, Alex?
Why is that the case? Why is that the case? I'll just stop sharing because I need to quickly do something. But that is the case because we should look at our training data once, otherwise it just becomes, sorry, look at our testing data once, otherwise it becomes part of our training process.
It is the most common mistake that we all make, Alex and I included, is that, so like, the reason is, right, is imagine you've got a data set, you're going to split it into training and test sets. There might be some very specific features about your data that end up in your test set that you intuitively start to account for in your modeling process, and then that contributes to overfitting. Yeah. Humans, we're very good at pattern recognition, and we start to like make changes to our data when we notice patterns, even when we're looking at our data early on. So the earlier you can separate that test set and ignore it, the better. You obviously will need to check it a little bit because you need to make sure that, you know, you're not going to crash stuff, or you want to know what variables are and stuff like that. But the earlier you split it, the better, generally. Less likely to overfit.
So I'm going to share my screen again now, which I can't find the button for. That's great. Okay, so what's wrong with what I've just typed there? There's something I haven't done, because I could run that. I could just run pub split. Oh, I should also set a ratio. That's wrong. I haven't told it what, remind myself what the name of the parameter is, prop. So by default, it does a 3/4 proportion, but I want a 4/5. So yes, thank you, setting a seed. So I'm going to do this in a slightly more, so David raised an interesting point with me, which is when we set a seed, lots of people choose the same seeds of like one. And that's fine, except that it means that everybody's working with the same random data, which then isn't really random anymore. So it's probably better to, setting a seed always, like, you're gaining reproducibility at the expense of maybe some rigor in terms of guaranteeing that what you've got are truly, you know, well, they're not truly random, but that what you've got are approximately random. That's the trade-off you're making. And in most cases, it's worth setting a seed, even though that trade-off ends up happening. But it's better to try and use a seed that, you know, maybe nobody else has used. So I'm going to go to random.org, and I'm going to generate a true random number to use as my seed. And I'm going to hard code that. So it doesn't matter that this is generated randomly. I have done 8651. So I'll now go back, and I'm going to set my seed as 8651, and that's my seed. And that will hopefully, it's good practice to do that, just because it means that you won't keep using the seeds as everybody else. Same seeds as everybody else. Yeah, certain numbers are particularly common. 1 is particularly common, and other small integers. 42 is particularly common because of the works of Douglas Adams. I would imagine other numbers that crop up in popular culture I would imagine 24601 occurs far more than 24600 or 24602 for musical theatre fans / Victor Hugo fans. What does the seed do? So what a seed does is, when we're generating random numbers in R, we're not really generating random numbers at all, because computers can't really do random, truly random, without some sort of external thing. Computers are inherently deterministic, and they are applying rules to produce things. So what computers do when you ask them for random numbers in general is they produce pseudo-random numbers. They produce numbers that are not actually random, but pass various statistical tests that make them roughly equivalent to random numbers, that look random, essentially. And they usually base that on the time, a few things like which operating system using, whatever, but the generator often incorporates into that as a thing to sort of decide how to start generating. It basically applies a formula, a complicated formula that spits out numbers that look random. And it usually bases what number it sort of initially puts into that formula based on what time you run the code, because that's close enough to like, well, it's going to be different each time, right? The problem with that is that every time somebody knits this document, they'll get different results. So they won't be able to reproduce your analysis because they won't know which time you ran it. They won't be able to force it to go back to that time. And this is like split-second timing, so you can't even like fiddle your clock very easily to do it. So what we're doing here is saying, okay, let's just set a seed for our random numbers, so a random split of the data, and then anybody else who runs this code will be able to hopefully run it.
In other words, that formula, the very complicated formula that creates this pseudo-random thing, needs an input. So it needs to start somewhere.
Yeah, it needs to start somewhere.
We're telling it where to start. And it'll always start the same place. So if you run it, if I run it, if Alex runs it, we're going to get the same output because we're all starting at the same place.
Yeah. But what I've done in order to set that is I chose a random number to start it from. So I chose a genuinely random number to start it from. And actually this website, there's no seed involved in this because this is, this website uses, I can't remember what it uses now. Atmospheric noise, there you go. So it literally has things observing the world and the true randomness that's actually in the world to get data. And there's loads of different ways you can do this. But there are various things like random.org that supply truly random numbers for when you need that. I think I mentioned this last week, but there's a tech company in America that does it based on pointing cameras at lava lamps. That's quite fun. So we're going to do our test trains, but I'm actually going to add one more option to this, which is the strata option. I'm going to put strata equals country. The reason I'm going to do that is that England has far, far more things in these data than the other two. And I kind of want my split. I don't want to end up with so Northern Ireland we're filtering out, but Wales and Scotland have a relatively small number of council areas. I don't want to end up with them being massively underrepresented in either of our in our test data or our training data. So I'm going to stratify by country. So roughly what that means is I'm going into each country and sending 80% of them to the training data set and 20% to the testing data set. So that's possibly useful if you have categorical variables where some of your observations in the categorical variable have a relatively small number of things relative to others. And that's the case here. England has far, far more than, and again, with more time and better data or a lookup table, it probably would have been better not to include England at all, but to include the English regions separately. But I didn't do that. The English regions are a bit closer in population to Scotland, Wales, and Northern Ireland. Okay, so we're going to do our pub split, and the standard thing to do here is pubs train is training, pubs split, and pubs test is testing pub split. So these, I'm going to line those up because it looks a bit near. The functions testing and training aren't very exciting functions. Literally what they're doing is extracting bits of this initial split. So if we run the first line where it makes the split, I didn't actually set the seed because I didn't run that line of code. Oops. There we go. So if we look at our environment here, what pub split is at heart is this rather complicated list. and all testing and training do are extract the bits that we wanted. Okay, so we can now try fitting a model to the training data set. So let's do that. Let's run our workflow on the training data set. And it's really straightforward to do that. It is pubs flow, that's our workflow, and we want to pipe into the end of that fit data equals pubs train. So it's worth noting that pubs flow has just been assigned the output of a pipeline, right? So if we really wanted to, we could copy and paste all of this and like stick it on here. We could do like that would do exactly the same thing as what we're about to do, but we don't do that because the whole point of defining a workflow is that we can use it multiple times. But that's really what's going on, is each time we're starting with a workflow, then adding a model, then adding a recipe, then fitting the data. And I forgot to run the line that defines the training data set. There we go. So we've got our model, and I didn't assign it anywhere, which means I can't look at it, but let's have a look and see what's going on. So we're nearly done. Keep not running the relevant lines of code. There we go. So it's still including Northern Ireland as a country. There's a sort of, I think I could fiddle that to make sure that it just doesn't appear in the output, but it's probably worth keeping it around anyway, just to remember that we removed it and that we're just not trying to predict things for Northern Ireland. And then what have we got going on here? So we've got that in our model, we have that there's an intercept, and then we have that our model predicts that, shall we say, our model predicts that as median pay increases, the number of pubs per capita will decrease. That was what we saw before. As population density increases, the number of pubs per capita will decrease. I suppose that makes sense in less dense areas, keeping all else equal, I should say. That's really important as a caveat, keeping all else equal. And I suppose that would make sense as the number of pubs, it's only a very slight effect, and we're not talking about significance here, but it's not a significant effect. But I suppose that would make sense that if population density increases, you might not need as many pubs to cover everybody that wants to go to them, I guess, but fine. Now, two of our predictors are actually correlated to each other. And that's why we're getting, so actually this is a good cautionary example of what David was saying. Life expectancy female and life expectancy male are highly correlated, as you might expect. So what we're getting is that the model is taking life expectancy male as kind of the one that it thinks is significant, and it's saying life expectancy female doesn't really have much of an effect on top of that. So that's what's going on the p-values. Again, we're not worrying too much about significance, but that's probably a thing we should have accounted for. We might have wanted to have terms that were like life expectancy male and difference, or life expectancy female and the difference between the two. That might have been a good feature engineering thing to do. So in the write-up, I might do that if I have time. But it's predicting that keeping all else, and that's what makes our analysis a bit weird, because it's saying that keeping all else equal, the number of pubs decreases as life expectancy female increases, but increases as life expectancy male increases. And that doesn't make sense. There's no reason that should be true. And that's because we can't really keep all else equal, because we know that life expectancy female and life expectancy male in real life are highly correlated. So that's exactly the problem David was saying earlier. If you have highly correlated predictors, it makes your interpretation of them all really quite difficult. Country Scotland was saying that then as a sort of baseline, we have a lower predicted number for Scotland. A higher number in Wales, and a lower number of somewhere is not coastal, which actually fits with my hypothesis that coastal areas are likely to have more pubs. Just to show you one last thing, because I know we're very close to the end of the time, if not at the end of the time, but I just want to show you that we should maybe take all of this with a pinch of salt, because if you look at our R squared, it's 0.2. And if you look at our adjusted R squared, it is 0.183. I'm going to stop there. There are some questions, but I'm going to take that after the recording because it's slightly sideways thoughts on the course. Thank you for watching, if you're watching the recording. And there'll be a write-up of this going online at some point, hopefully tomorrow, Monday at the latest, I would imagine.
Thank you, everyone. Stick around if you got any more last-minute questions. Thank you very much.